Alors, bonjour, rebonjour à tous. J'espère que vous allez bien. Bon après-midi. Bienvenue à MTL Connect, la semaine numérique de Montréal. Hello, welcome back. We are at Studio 2, the main stage of MTL Connect, Montreal's Digital Week. Je suis votre animateur Armand Afkami de la société Kelvin Zero. I'm your MC, Armin Afkami from Kelvin Zero. Un plaisir d'être avec vous aujourd'hui. On passe au deuxième segment de la journée ici dans le Studio 2 où nous allons parler de technologies disruptives. We are in the second part of our programming here in the main stage, the Studio 2, where we will be talking about disruptive technologies. I cannot wait to present the next keynote of this segment. I hope that you're ready. We're going to be talking about Quantum 2.0. J'ai vraiment hâte de vous présenter notre conférencière Keynote. On va parler de quantique et j'espère que vous êtes prêts. Alors, sans plus tarder, je veux introduire notre conférencière. So, she's an award-winning quantum physicist and author who has made foundational contributions to quantum science and communications. She's the founding director of the Laurier Center for Women in Science. She's a TED Senior Fellow and currently serves on the scientific board of the UNESCO International Basic Science Program. She's also the author of Clues to the Cosmos, and she still dreams of going to space. Please give a warm welcome to Shohini Ghose.
Thank you. Bonjour. So I want to tell you something about quantum computing today, which I know it sounds a bit complicated. Who is an expert here? Who is not really an expert? No problem, don't worry. Since that's what I figured, I thought we'd start with maybe a small warm-up exercise. And it's really easy. So ready? Let's do something really, really basic. Okay, here we go. Here's a question for you. It's 2022. So let's take the number 22 and try to break it up into two smaller numbers. Not hard. See, you're already starting your first steps into quantum. This really is related. It's not a trick question. Who wants to give me an answer? What times what is 22? 2 times 11. You guys are super smart. You're already ready. Quantum is going to be easy after this. You ready? Now you're warmed up. You want to try something a little bit more? One more small exercise. Very easy. Ready? Okay, ready? Okay, here we go. How about this one? No? Oh, come on. It's not that hard. I know you know. You know this. That's a great starting point, actually. This, if it was 1 times it, you're right, it would be a prime number, right? In fact, it's not a prime. It's something we call a semi-prime, and nobody should feel bad if you cannot solve this, because it's actually really, really hard to do this. You can try it on your computer. You can try it on your fancy supercomputer. You can try networking all the supercomputers in the world and try to do this. And that's what people did. And in fact, this was a challenge that was put out, and somebody solved it. This was solved, and here's the answer. Obviously. You would have guessed that, wouldn't you? Yeah, so this is a very, very hard problem. It took lots of supercomputers linked together, smart algorithms, smart people, clever guessing to get the answer to this problem. This one is called RSA 576. This number has a name. It's so special. Why? RSA 576 stands for a number that has 576 binary digits. In fact, if you count up all the digits in this, it's not written in binary. It's written just as regular numbers. And if you count it up, you'll see there's 174 digits in this number. It's not the largest number that people have cracked. The largest, currently, I believe, you can Google it, by the way, the largest such RSA number is, I think, 250 digits. So a few more than this. But you go to 251, nobody's done it. It's that hard, no matter how much computing power you have in the world. So see, you're already really warmed up. We're already into one of the hardest problems we know of, factoring a large number. Why is that important? Well, it turns out we use it. We use the fact that factoring is hard. A hard math problem is good. Why? Because if you guys can't do it, hackers can't do it either, no matter how much computing power they have. Which means if you can build encryption based on a hard problem like factoring, you're good to go. Your passwords will be safe. Your information will be safe. And RSA, which is a factoring-based encryption method, is in fact what's used today to actually protect all of our information. It's one of the most common standards currently used. So this could be a problem, though, if tomorrow somebody cracked this, right? So yes, it's great, but no, it's bad because it's based on mathematics. And mathematics means there's maybe a clever kid out there, and she'll grow up, and in a few years, she might crack this. So can we ask, is this actually safe or not? That's where quantum computing comes in. Turns out, in fact, somebody has pointed out that if we could build quantum computers, you could actually factor large numbers in minutes. And that's why this is a really important area to focus on, because all of our data is now vulnerable. So what is it about quantum? A quantum computer that's better than all the supercomputers in the world to factor numbers. Why quantum? So I want to give you an idea of that. Without getting into more mathematics, by the way, that's it. No more mathematics in this talk. Yay. You can all clap. But we will be talking about numbers, of course. So computing, by definition, has been based on some very specific ideas that are actually really easy. No matter what you want to calculate, whether you're using your fancy laptops or supercomputers or what NASA uses or all the cryptography done in the world today, everything actually is kind of ridiculously simple. Why? Because it's all based on zeros and ones. What I'm going to tell you is that's it is simple, sure, but it's a little limiting. Really? 0, 1, that's it? What if we could do something more than just take a 0 and make it a 1, or combine zeros and ones, or flip from 0 to 1 and 1 to 0? I know that this whole conference is focused on digital, which is really what zeros and ones are, digital information. What I'm here to tell you, that's not the full story. There's so much more. So next year, I hope you have a conference that's beyond digital, because that's where we're going with quantum. Quantum computing is different because the foundational principles of how we're doing computing is changing. Quantum is an expanded version of this digital binary kind of computing. So I want to tell you why. Just one step before that, I have to tell you a little bit about why it's a bigger landscape of computing. And this comes from something you've probably all heard of, this idea of, quantum uncertainty, right? Heisenberg uncertainty principle. What does that mean? We know that given a particle like a photon or an electron, we cannot precisely describe every single property of that particle. It's kind of like, think about your GPS in your car. You're driving, you look, or your maps on your phone, Google Maps or whatever you're using, and you can see where you are on the map, and you can see how fast you're going, and you can see what direction you're going to. It's all there, not a problem. Well, if you try to make a GPS for an electron or a photon, you can't do it because you will never be able to know exactly where the electron photon is at the same time as knowing how fast it's moving and where it's going. Which is kind of weird. What is that? Does it mean that it's actually something we don't know, or does it not actually have a specific location? Or is it because it's in multiple locations, which is what you may have heard describing electrons and photons and these quantum particles? Well, the mathematics actually doesn't specify. The mathematics tells us that precisely knowing every such property is not possible. Why not? Meaning, is it because it doesn't exist, or because it's at multiple locations, or it doesn't have that as a property at all? Don't know. So that's where all these philosophical questions comes in. However, weirdly, the mathematics is perfectly precise. So it's a little bit hard, of course, to imagine this kind of a scenario in our world, because we have regular GPS, it works, we know where we're going usually, unless Google Maps fails or whatever. But the reason we can do that in our world is because we are at what we call a macro scale. Once you drill down to a single electron or a single electron or photon that's not talking to anything else, the rules are different. These particles don't necessarily have a specific identity. They have this really fluid kind of identity, which I kind of like dreaming of a world where you have this, extra flexibility in terms of whether it's location or your speed or your direction. Wouldn't it be nice if we lived in that world? We don't, but the electrons do. Very strange. We cannot imagine it. So for a long time, this idea of quantum uncertainty was seen kind of like the weirdness that must be ignored. We know the math, so let's calculate stuff. We can build cool lasers and all kinds of gadgets and technology, but let's ignore the quantum uncertainty as much as we can and move around it. What's changed in quantum, what we call quantum 2.0, is let's not ignore it. Let's embrace it and say, well, this is a nice, different type of description of maybe not even reality. Who cares? But what if we could harness this idea of uncertainty and say, put it into ways of processing information in a more useful way? And that's why quantum computing is not even starting from regular precise values of 0 and 1. It's moving away into this larger possibility space where maybe you don't know everything about a particle, but that's okay. That's not necessarily a bad thing. It's more powerful. How? Okay, so let's think about it in the language of computing itself. Normal computing, 0, 1, combine them, add them, subtract them, make them multiply together, all of our standard kinds of operations. Quantum, if you allow for this idea of uncertainty, actually translates in the language of zeros and ones to a spectrum, meaning there's some probability that maybe this quantum particle, which we call a quantum bit or a qubit, some probability it's 0, some probability it is 1. We don't know until we observe, which may sound really weird, meaning if you don't know, how are you going to do some precise calculation like that large number? How do you factor a large number without knowing what your actual individual values are? Sounds weird, doesn't it? This is why it's so weirdly counterintuitive. Turns out that letting go of precision while you're doing a calculation is powerful. Why? Well, one way to visualize it without going into the mathematics is to think about 0 and 1 as 2 points on a landscape. And if you have many bits of information, there are all these points. And digital standard calculation is like being able to jump between points and make a path to go from point A in your computational space to point B, which is your answer. And you jump around. But in the quantum computing landscape, where you don't have just the points. You have everything in between as well, because you're allowed some superposition, meaning a combination with some probability of 0 and some probability of 1. So you have more knobs. That's what's powerful about it. Instead of thinking of it as a problem, you say, well, I start my computation. I know that I have to get to a particular answer at the end, but I'm going to allow this imprecision, uncertainty in the middle to help me by flowing my probabilities towards the correct answer faster. So that's the broad idea, which is why you have to move away just from zeros and ones. And of course, jumping from zeros and ones is part of this larger space. So all of our current computing that we have, all current computers, are actually a subset of this larger quantum computing space. And all of this was actually figured out or noticed, this idea of rethinking computing and rethinking uncertainty as a good thing, like an extra knob. I'd say it was roughly in the 70s and 80s, and Canada played a big role in it, of course. You may have heard recently that some scientists were awarded the Breakthrough Prize. One of them was from Montreal, Professor Gilles Brassard. And the reason that this Breakthrough Prize was awarded was because these scientists pointed out one of the first examples of how we can use this bigger quantum uncertain space to do something useful. They didn't talk computing, they were looking at encryption. Remember we talked about factoring and using factoring for encryption? That's a hard math problem approach to encryption. What these scientists pointed out was that what if we don't use math to do encryption? Instead, let's use physics for encryption, meaning quantum physics. How? Well, let's go back to this idea of probabilities of zeros and ones, where we don't know everything about individual particles. What if we encode our information, our secret keys, our passwords, using this idea in such a way that if somebody wants to copy or hack the information, what they would have to do is, one thing they can't do, they can't copy the information perfectly. Why? Well, there's no way to precisely copy a particle because of the probabilistic nature of the information. And two, if they try to, you can actually detect it. That's another sort of free sort of resource you get out of it. Which means if you can encode the information using quantum uncertainty, then you can protect it from any kind of hacking. No matter what computer the other person used, no matter even if the hacker has a quantum computer, in that case, they might use their quantum computer to try to attack your information. But the only way to protect against a quantum hack is through quantum encryption. So here's a way to fight quantum with quantum, right? So this was what was pointed out in the 80s. And over the years, the idea has grown and grown and grown. And now we have a quantum revolution, which we call Quantum 2.0, which is to try to apply these ideas and build new encryption and new computer technologies that work in this bigger space. So that's what is so exciting, that we're right in the middle of that kind of a revolution. And there's even more interesting knobs we can use. So another one I think everybody has heard of. It's like become the most common sci-fi thing, right? It's called quantum entanglement. Who here has heard of quantum entanglement? Yeah, most people have heard in some capacity. What is quantum entanglement? Well, it's really this idea that individually, if you think again with quantum bits, qubits, if they are in some superposition, this fluid, uncertain state, what happens is that they can connect to each other. Let's say you have two of these qubits. Either you can make them interact, or maybe they have already been created in pairs in the past when you first create the qubits, in such a way that they get linked. So individually, they still have this uncertainty. You don't know whether they're 0 or 1. But if one of them is observed to be a 0, then the other one is definitely, instantly also a 0, no matter where it is in the universe. So it's this instant connection that they seem to share that you cannot separate them out from each other. We know that individually, absolutely quantum uncertainty still applies, but jointly, the information is precisely encoded. They connect. And that kind of balance of quantum uncertainty and superposition combined with perfect connection is actually what quantum entanglement is. And in fact, this year, the Nobel Prize was awarded for experiments that used the idea of quantum entanglement and did experiments to observe this entanglement and to prove that this connection is stronger than just everyday connections like, left glove, right glove, or pairs of socks. Those are also kind of connected. But quantum particles, when they get connected, they're not like socks, and they're not like gloves. They are even more connected than that. And that kind of a connection can be used, again, as a knob. If we know how to cleverly control entanglement, it becomes like a fuel that drives quantum computing. One of the kind of more, again, science fiction tasks, but it's real, that happens because of entanglement is something called teleportation. And you can actually distribute entanglement across large distances. It's already been demonstrated using satellites. So back in 2016 already, China launched a satellite used for testing quantum experiments. So this particular satellite actually can generate these pairs of entangled photons, which are particles of light, and send them to different stations on Earth. They can be used then to generate secret keys, for example, or to actually do quantum teleportation. So I love this picture because I always try to have a Star Trek image in all my talks, but any excuse. But you cannot actually do Star Trek level teleportation, sorry. It's a nice image, but what quantum teleportation is teleporting information from one location to another. Like these, as I said, you encode your message, for example, in these entangled particles. Using entanglement, you can actually move the information from one location where it disappears in one location, and it's recreated in another location. It's not instant, so that's also not part of what's allowed with quantum, sadly. There's always a speed of light signal that has to also be transmitted, but it's a completely new way of transmitting information from one location to another. So that's what quantum teleportation is, and it can be used for building maybe a future quantum internet with satellites that sits above or as an addition to our current internet, or it could be used actually for quantum computing. By teleporting information, you can build algorithms that can perform certain tasks better. So that's part of why entanglement is so exciting. So this is, I've shown you a picture of Star Trek. This is really now getting into science fiction, right? Is any of this real? That's the real question here. And the answer is kind of yes. It's early days. Remember back in I think it was around World War II when early computers, the first regular computers were being built, right? And then those became, the ENIAC and these, I call them ancient. It's not that ancient. But let's say, about 50 years ago when, regular computers were being developed, they were the size of a room. This is not a picture of ENIAC, by the way. This is a picture of IBM's quantum computer. But it looks a lot like those old pictures of rooms full of, controls, right? So in a way, that's appropriate because I think we are kind of at that stage in this quantum 2.0 revolution where Small prototype quantum processors do exist, such as the one in this photo, where you see the woman walking towards that white cylinder. Inside the cylinder is the quantum processor, but it's not the full cylinder. All that stuff, if you open up the cylinder, you see this beautiful chandelier, for example. This is not even an updated photo. I think they've changed their their setup a little bit now. But generally, all of this fancy sort of hardware you see, it's mostly for control and for cooling this computer down. Because the actual processor, the chip, if you like, you can't actually see it in the photo. It's very small. So everything else is super impressive stuff is just for controlling and cooling. Why cooling? Well, quantum computers have errors, just like your computers. So every time you use your laptop, sometimes it freezes, right, completely. And usually it's because it overheats and things like this. But actually, even when it's working, it's not because somehow it's error-free. There's always some correction happening in the background. You just don't see it. But the reason you send, emails without too many worries and you can do all your calculations is because there's always error correction. There's no such thing as a perfect system. Quantum computers, same thing. They have errors, but their errors are much, much harder to control and correct. Obviously, you want to first minimize the errors. What is an error for a quantum computer? Remember I said, well, a quantum bit can be a 0 or a 1, and it's in this bigger space, and it has this fluid identity. Well, that's its superpower. So when that quantum bit gets heated up somehow or gets messed up, because something that you're not controlling in the room, maybe it's, there's, I don't know, a passing truck, causes some vibrations or something. Anything like that. If it disturbs the quantum bit, it actually loses its superpower, meaning it just becomes a regular 0 or a 1, like a bit. And that's boring. We don't want it to become a regular bit. We want it to keep its fluid identity. Why? Because that's what we're using to speed up the computation. So anything that kills that is a bad thing. So that's very hard because every single tiny little bit of interaction with anything outside of your computer will kill that qubit and make it into just a regular bit, which is really weird, but that's the reality. So what we need to do is keep this system so cold and as much in a vacuum as possible so that it does not interact with anything. And when I say cold, I mean colder than outer space. So it's hard to do that, which is why you have these huge rooms full of equipment and controls and graduate students who do all this hard work to keep this computer running. Does it run? Well, yeah, kind of, sort of. Different companies are working on different types of approaches to build a quantum computer. Nobody's won the game and built that fancy, powerful, large-scale quantum computer yet. Everybody's claiming they'll do it by next year, and then the year after. So if you Google, for example, IBM, they actually have put out a roadmap of when they will build a larger scale. Next year, they claim they're going to build something that's large enough to do a problem that has never been cracked before. So who knows? It's early days. A lot of problems. As I said, the challenges of building something that has no errors and can be scaled is huge. So are we there yet? Not yet. But I can show you that you can do some tests even on small computers. What I'm showing here, it looks all fancy, but it's really a circuit diagram. It's like a computer code for a quantum computer. And what we did in my research team is we can access the quantum computer on the cloud. This is IBM's machine. And we said, let's do a test. Can it do something better than what anybody can do today? Well, we set up a game where there were 3 players in the game, and we simulated it on this quantum computer. And the 3 players have to collectively make a decision, kind of like, should we, buy this particular stock, yes or no? So it's a yes or no kind of decision. They're given some information, but they're not allowed to talk to each other. they are allowed to share entanglement. So they use entanglement, they can't talk to each other, and they have to make a joint decision. If they use entanglement correctly, then their correct decision, it's of course a test problem, so we know what the correct answer is. So they can make the correct decision 100% of the time. If we try this many, many times, they should get it right every time. If they don't have entanglement, and they're not allowed to talk to each other, and they can only use regular computers, then they can make, at best, from guessing very well. The best strategy will give them success 75% of the time. So there's a difference. And we wanted to test, will this quantum computer that lets entanglement be generated, can it give me an answer 100% of the time that's correct? That was the test. And what we found is that, in fact, this is data from the actual quantum computer. The orange line is the theoretical best case, 100% success. The blue is our test on regular computer. That's about 75% success. And then the gray is the data from IBM's actual hardware, the quantum processor hardware. And you see it's not at 100%. But it's not at 75%. So it beats the regular computer, but it has so much error that it can't hit 100%. And there's no error correction. Currently, the processors that exist, no matter which company we talk about, nobody is actually doing any error correction. It is possible, but very hard. So nobody's doing it. So without error correction, this is what you see. So, it's really, how do you evaluate it? Well, it's really about showing that you can do something useful. Entanglement is helping, but this computer is nowhere near a clean, robust, large-scale machine yet. But it's kind of exciting to try to test it and poke it and see what it needs to do better. There's clearly some indication that in the future, if these very significant hardware challenges can be addressed, we can perhaps be in a regime of large quantum computers, but that's a little scary, because that's when all those factoring-based encryption standards, all of them are gone. And it could happen the minute somebody builds it. What are you going to do? Are we going to scramble to suddenly change everything over? Or should we be planning for it now? Something that we as a country and all countries around the world have had to think about. How do we change over to a more protected system? We know the answer. Let's do quantum encryption. But we're not there yet. So I just want to perhaps give you, in the final few minutes, a quick overview of what kind of tasks can a quantum computer help with. Not everything. We know only of particular things that a quantum computer using entanglement and superposition can do better. Not everything. So, now I have a timer. Yay. The regular computer is not working very well, so we need a quantum timer. So, what can we do? Well, I've told you one example. That is quantum encryption. So communication networks are evolving and changing all the time. And some countries, as I showed, China and others, are already moving strongly towards a quantum-based communication network. Is it completely hack-proof, like I said? Not yet, because there, too, there are errors. So a really smart quantum hacker could still hack the existing quantum networks that have been set up. But you got to know a lot of quantum, and you got to have some resources. So for practical purposes, those kinds of networks are actually secure. But they're very small scale, so to get to a global network that is like a quantum internet will take a long time. But that's one of the areas of work, both at the research level as well as commercially, that's happening. I put health on here because these small quantum computers that exist today, they can't do a lot. I showed you, right? There's a lot of error. But turns out that there are small problems that are worth solving. For example, in healthcare, when we are doing drug development or trying to figure out how different molecules interact with other molecules and so on, chemistry, I'm not an expert, as you can tell, but I know it has to do with molecules and electrons and how they behave. And to actually calculate the properties of every electron in a molecule with maybe 100 or so atoms, again, is one of those problems that we don't know how to do. So you know how with factoring beyond 250 digits, we have a problem? Well, with molecules, having a molecule that's like 100 or 200 atoms, can't do it. So if we wanted to design complex kinds of pharmaceuticals, we would need something that would be better at calculating these things and helping with drug development, and not just drugs. Molecular chemistry is obviously used for materials design, building solar cells, clothing, smart clothing, so many things. So understanding chemistry or being able to efficiently calculate chemical properties, huge, huge area. Imagine if we could have small quantum computers do better than what we have now. Just a bit of an advantage, and then you use all the power we know we have now with regular computers, put them together, lots of benefit. So that's another area where there could potentially be benefit. Things like supply chain and environment. These fall under a category of problems that involve some kind of optimization, meaning, for example, with supply chain. If you want to find the best route for delivering, whatever, your goods from point A to point F or X, but it has to go through B, C, D, E, F, G, blah, blah, blah. Right? And you have many different constraints like, the weather, the traffic flow, the, volume and the demands and cost and energy, many, many parameters. So if you have a multi-parameter problem like that, turns out that we know that certain types of quantum approaches can help with optimization. So here's a way to think. If you are in a company where you're wondering, can I use quantum to improve anything? Well, the things that we know for sure would be useful are problems where you're trying to maximize something or minimize something, improve something which has many parameters in it, search for some particular outcome. For example, in climate data, you're trying to find certain patterns. Maybe that's another sort of problem that can be reframed. So optimization is actually a very large class of problems. Many, many problems can be framed mathematically in the language of optimization. So that's an area which would require much larger scale computers. We don't have that level of quantum computers today. We don't even know if we ever will, to be honest, because there are so many hardware challenges. But perhaps it may be possible. We will have to wait and see how the design and engineering evolves going forward. Similarly, the reason I put finance is because there are many, many optimization tasks in finance and also searches and stochastic kinds of processes that are well suited to probabilistic approaches. So that's kind of giving you more of a broad categorization of the kind of problems. The truth is, if you give me a problem, let's say that you're dealing with in your company, and ask me, can this be improved with quantum versus our regular computers? We as researchers don't have a general recipe. So that's important to keep in mind. I can't just look at it and say, oh, check, 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 this is quantum. There isn't such an approach. So it's the kind of area where we're still learning what kinds of problems do work, what kind of problems don't work. We have hints of important problems that we can solve, but there's a lot more work to do, and given all these possibilities, there's a lot of funding and investment. This is a lovely diagram I stole from a Swiss report, which shows all the different government-level funding that's been invested in quantum over the years. It's not complete because it only goes until 2019. But over the last couple of years already, there's been much, much more that has been announced globally, including in Canada. There was over $360 million that was announced. But that's nothing compared to other countries. So Europe, the US, India, everybody has already announced government funding. This is public sector funding, over $1 billion, everything dwarfed by China, who is well into the tens of billions of dollars of spending. That's on the public side. Private sector, similarly, there are huge numbers of companies, both large and small startups. This is a rough division into those who are working on the front-end software and algorithms and just user-friendly apps versus looking at building the hardware. We have several companies in Canada. I'd like to mention, for example, Xanadu is a company that's based in Toronto that has been making some really exciting progress in being able to show some quantum advantage. D-Wave is an early player based in Vancouver that is not working on the full quantum hardware, but so far has focused on these quantum optimization kinds of problems. So their hardware has been used to test that. Now, of course, there are much bigger players around the world. Google and IBM, everybody's claiming quantum advantage. You should probably be taking all of that with a grain of salt because there's a lot of challenges, as I mentioned to you. What's really exciting is that these are the main quantum computing kinds of companies, but there's a lot of sort of associated adjacent players. Tech companies working on better photo detectors, or as I said, these chemical companies looking at pharma versus medical companies that are trying to develop better sensors and imagers. So there's lots of exciting work. This is by far not a complete list. There's many, many others. And again, if you want to put dollar values to this, estimates currently are in, again, tens of billions of dollars of potential market activity. But again, I'm not an expert on the quantum finance piece here. I will mention that recently, I think at the end of last year, the first purely quantum computing company went on the stock market. So this is the first publicly traded quantum computing company. It's called IonQ, based on the fact that it uses ions to build quantum computers, which is exciting because it means that they're making real progress, I assume. You might notice something else, though. I went on their website and I looked at their leadership and their board. I was not super happy, because you might guess why. This is not necessarily a good representation of everybody who might be interested and have a voice in this kind of a company. To be fair, this list I pulled from their website in June of 2022. As of July, there was another addition to the board. It was a woman. So we have one woman among all of these board members, but that's not ideal because it really has to be better than that. But I don't want to end with this sort of down note. So I want to show you a much more fun photo. This is one of my favorite photos because all the women in this photo are physicists. This was a gathering of women in physics that we hosted in Canada a few years ago. And these women are from 50 different countries. They were not all working in quantum, but there's so much talent. There's a workforce out there, also in Canada. And we will need everybody to be involved if we're really talking about a social revolution that can change healthcare and transportation and information security. So that's why I think it's important to think about this piece of the puzzle as well going forward. And during the pandemic, I mean, we all came up with new projects, right? So for me, one of the projects I had was I started writing these little haikus about science. So I thought I'd end with one of the haikus I wrote about quantum, because I am that nerdy. So here we go. That's my haiku for you. Let us be quantum, entangled across space-time, hearts and minds as one. Thank you.
What can I say? That was amazing, Shohini. Thank you so much. I think it's time for some questions from the audience. We left a lot of time for you all to exchange with Shohini. I think this is a great opportunity. I see someone who's venturing. There's two microphones here, one on the right, one on the left. First question.
Hi, my name is Vincent Doré. I work for ICED. So my question is, how would you say the world is vulnerable understanding that the technology is not there yet, but understanding that, as you said, pretty much everything that we're trying to protect could be vulnerable. So I was just wanted to know what's your thought on this.
So, okay, the answer generally is that we already know that if a quantum computer is built large scale, then definitely it can hack current encryption standards. We know that for sure. We can prove that mathematically. Will a quantum computer of that scale be built? We don't know that for sure as yet. But because of all the development happening, I think it's prudent to assume that at some point it might be built, and we can't wait to answer for sure yes or no. Because even the possibility has already undermined our data security. Because knowing that it could happen already means that we can't trust our security. So does that mean we are vulnerable? I would say yes. And let's also keep in mind that everything that currently exists in encrypted form, if somebody has been just copying all that data in encrypted form and storing it, waiting for the quantum computer to be built, then they can go back and hack all of that, and there's nothing we can do about it. So that stuff is already vulnerable for all time. Nothing to be done about it. So I know it's bad news, but let's start doing something about the future. Right away. Tomorrow.
Tomorrow. That's an invitation. Let's protect.
I hope everybody's really scared. Sorry.
Any other questions? I think, again, this is a unique opportunity to ask Shohini. Any other questions? Impossible that you have no other questions on this presentation on quantum. That means everyone's an expert, everyone caught it? I hear laughter. Anyone else at all? Okay, I'll venture and ask a question. I asked someone else earlier this question. Who are the leaders in quantum in the world right now?
Oh, I'm going to get into trouble if I try to say, oh, you're a leader.
Trying to get people in trouble. That's my job.
Oh, my gosh. So, well, one thing that I will say, as I mentioned before, is that Canada has already been an early leader, going back, as I said, to the 80s in terms of the ideas behind quantum computing. Plus, we have real quantum hubs all across the country, starting from BC, Calgary, Waterloo, Quebec, and going out east also there are researchers. So there's a huge growing ecosystem of research and development in Canada. Mm-hmm. And there are, by certain metrics, we're certainly still ahead in terms of things like, publications and patents that are, being developed here. That being said, what makes the news usually is this competition between, Google claiming that they have quantum advantage because they solved a problem faster than anybody else. That was done a couple of years ago. But even in that sphere, I will say that very recently, this Canadian company Xanadu made an announcement and published this really great paper where they showed that they beat Google. But there's absolutely leadership, as I said, in China. Europe has strengths as well. So it's really a quantum race, kind of like the old space race.
So in the Quantum Olympics, Canada's got a few golds.
So far. But we must not sort of...
We can't stop there.
Yeah, exactly. And at some point, the rest of the world will catch up.
Excellent. Thank you, Shohini. Any other questions? Des questions, même en français, ça va me faire plaisir de les traduire. Si vous en avez, quelqu'un, je vous invite. On est ici en présentiel, je vous vois. Je sais que vous avez l'air d'avoir des visages qui veulent poser des questions. Gênez-vous pas. Ah, je veux monsieur peut-être? Ah, oui, OK. Yeah, merci. J'aime ça, le monde qui participe.
Bonjour. Petite question concernant une entreprise qui a présenté au MTL Tech Awards des modules pour améliorer la communication quantique. Je me demandais, c'est quoi le meilleur moyen de transmettre l'information quantique? Est-ce que c'est une information qu'on a? On parlait tantôt de la téléportation, mais outre ça, la fibre optique, c'est-tu assez ou ça prend plus éventuellement?
Try to translate the best I can. He was mentioning that at the MTL Tech Awards that were presented on Monday, there was a Quebec or Canadian-based company that is working on communication methods for quantum, and he's wondering what are the best ways for quantum communication. I know we're talking about teleportation, but can fiber optics still be good enough to communicate quantum? C'est ça? Yeah.
Absolutely. So keep in mind that building quantum-based, for example, secret keys for making things safe and encrypted, we're still talking about transmitting light particles, photons, which is what optics is.
Yeah.
So it's still fiber optics based, but the problem there is we can use current networks, but we have to be very much more able to control things at the individual single photon level. Currently, when we send signals, we're also sending photons, but we don't care if it's 1 or 2 or a million, really. But now we have to look at that individual level. So yes, we can use fiber optic networks, but we need to make them much cleaner and much more precise in the control and how we can measure them, from what we send and what we receive. So yes, it's possible, but it's very hard to get it clean. And the second thing I will mention is that actually for quantum encryption, we can use entanglement, but we don't need to. We can actually, there is a way to make quantum encryption without entanglement and it'll still be secure. So that's a little bit easier because entanglement is one more thing to make that's new. So we don't need it. We can do it even without entanglement.
So technically, it's kind of like your USB-C cable. It's not going to go obsolete. So fiber optics won't be obsolete. It's just we need to adapt the way that we transfer.
We have to improve the technology, that we're currently using. It's not
Love
a
it.
new tech, but it's cleaner, better.
Cleaner, better. Love it. I see another question from the audience.
Hi, thank you for the presentation. My question relates to quantum communications. We often hear that China, Europe are a bit ahead of North America and Canada on that front. What would you think we could do to catch up and actually be one step ahead in terms of quantum communications? And I'm thinking mostly in terms of the networks that are being set up all around the world. There are plans to have one in Quebec, but I'd like to hear you on how you think it could be different from what's already out there and how that could give us an edge.
We do have, some efforts, as you said, in Quebec, as well as, satellite-based efforts to build what China is already doing. We have Canadian versions of that. What needs to be done is having a national infrastructure developed, which of course cannot be done just individually by province. So there's got to be some kind of a federal national plan, which also is being developed. There's already been an announcement of some funding for quantum technologies in general for Canada, but there's also, going to be an announcement of what's called a national quantum strategy. There may be an advisory board set up, but there's got to be some coordination. You're absolutely right. Other countries are doing things at the national level. And I also want to mention that, encryption and security, data security is only as secure as the weakest point, right? So it doesn't help if we kind of try to say, well, we will get it all secure. We all talk to people who are not in Canada. We send information outside. So I think maybe we need to even rethink this idea of Canada versus China versus everywhere else, because current encryption, by the way, it's a global standard. The reason RSA is so common is because it was set as a standard that the whole world has to get to. So I have a feeling quantum will have to evolve to that level, where we set these global standards and we all have to reach it. Otherwise, vulnerable points will mean we're all going to be in trouble. So will we get there? That I don't know. That's about politics. So who knows?
Thank you for the question. Yes, please, your name and your question, French or English.
Yeah, Roman, thank you for the presentation. It was very nice. So I'd like to know, do you have any thought about how the quantum computing will impact cryptocurrency?
Yeah, so there is some, we do know that some aspects of blockchain, for example, is vulnerable to quantum computers on a large scale, but there are, I think, approaches that could actually secure those particular aspects, but they have to be changed. So yes, quantum computing will certainly impact it, but from the other side, actually quantum could enhance things like blockchain and make them more secure, so that could help too. Overall, will cryptocurrency be, somehow therefore our next standard? Again, that depends on many other factors outside of the technology itself, so we'll have to see, yeah.
Thank you.
So good and bad.
Thank you for your question. One more or two more little questions. Une ou deux autres questions du public? Oh, oui.
Ooh, second.
It's a follow-up question.
Follow-up
Because
question.
we were talking about the factorization, and you were talking about it's one method. I was wondering if there's any way that today companies could use to protect themselves. You talk about China, how they're working on quantum tech for exactly that. So I was wondering, is there other method that maybe SMEs or business here today should be aware whenever they're trying to secure their networks and encryptions?
Yeah. So there are, I guess, you could have different approaches depending on your needs and your timeline and your resources. Of course, there are, different approaches. If you have, a multi-billion-dollar initiative like China, you could launch a satellite, but not all of us can do that. So instead, what can you do? Well, there are certainly other known math problems. Remember, I said currently the standard encryption is based on this factoring problem, but now we know factoring can be done by quantum. So are there other math problems that we don't know an algorithm in quantum for? And the answer is yes. There have been proposed new algorithms that are just math problems that are not factoring. Right? So these new math problems, we don't know if there's a way for quantum to crack it. But keep in mind that even factoring, we don't know, maybe there's even a regular computer, as I said, in the future, some smart kid might find a way to crack it. So whenever you go with math, there's always some possibility, unless you prove that this math problem is not solvable. If you just go with math, in principle, maybe in the future somebody will come up with a way to solve it, because it's a solvable kind of problem. With quantum encryption, the idea is that it's not a math problem at all, which is why, if China uses quantum satellites, then there is no math involved. So that's where they're going. That takes much longer, and infrastructure and changing the fiber optic system and launching satellites and so on. So in the near term, I think the idea is to go to other math problems, but they're not going to be secure forever. It's the risk that you take. They do exist, though.
Great question. Thank you. Shohini,
We're out of
our time is up. That was amazing. On behalf of MTL Connect and everyone here, thank you so much.
Thank you. Thank you.
Shohini Ghose, everybody. Thank you.
Thank you.
Thank you. Alors, merci encore d'avoir été ici pour la magnifique session. On parlait quantum avec Shohini Ghose. On va prendre une petite pause juste avant. J'ai quelques petites annonces pour vous. Alors, si vous voulez découvrir une prestation de cirque des 7 doigts de la main à 17h à l'étage 0, donc juste à la réception, juste en bas des escaliers, à 17h, ça vaut vraiment la peine d'aller les découvrir. Ils sont fantastiques. Sinon, nous avons également le Dôme qui est également à l'étage 0. J'ai pris quelques notes que je vais vous partager. À 15h, nous avons Startup Montréal dans le Dôme qui va faire une démonstration des startups avec lesquels ils travaillent en ce moment. Donc, ça vaut la peine de les découvrir. Demain, à 15h15, dans le Dôme, nous avons Philippe Longchamp de la Suède, nommé le meilleur enseignant du monde, qui va donner une petite séance très privée dans le Dôme, alors à ne pas manquer. On a un 5 à 7 présenté par National ici même dans la salle. Une chance de réseauter, jaser et parler quantum. Et demain, à 17h également, 17h30, nous avons le Café sénégalo-belge ici au Studio 2. On parle de plusieurs quantités de bières belges à déguster. En tout cas, moi, je vais y être. C'est un rendez-vous. Un grand merci à nos partenaires, donc le gouvernement du Québec et la Ville de Montréal pour soutenir MTL Connect. Et merci à vous tous d'être ici. On prend une petite pause de 10-15 minutes. On se retrouve pour un panel incluant Shohini. On continue la conversation sur le quantum. Merci, à tout de suite.